Hey everyone, this is the Composites project for Rob Ashcom, Nick Billeter, Matt O'Brien, and Jason McCrady. The purpose of this project is to make a composite spar cap that's 12 inches by 5 inches that has a varying thickness. Our group's constraint was that the matrix had to be an epoxy, but we had 4 design variables in the fiber volume fraction, the fiber type, the angle apply and stacking sequence, and the laminate type. There were 3 parameters to optimize in the thickness, the cost, and the weight. There are 3 things to consider when looking at the mechanical environment of the composite. There's a tensile load in the x direction of 8,150 kilonewtons, a tensile load in the y direction of 5,800 kilonewtons, and a moment in the x direction of negative 100 kilonewton meters. We chose to use a 105 epoxy with a 205 fast hardener manufactured by West Systems. Its properties, as seen in this table, are pretty standard for an epoxy and were all readily available online, which made it an attractive choice. We chose to use carbon fibers for this composite because of their optimal properties and low weight, compared to other fibers like glass or ceramic. The Toray 1700S carbon fiber was the cheapest with the lowest modulus and had moderate strength. The Toray T1000G carbon fiber was very expensive with a high modulus, but it had the lowest strength. The Pyrophil HR40 carbon fiber had moderate modulus and price, but very high strength. This table contains the mechanical properties and price of all 3 types of carbon fibers that we considered for this project. The testing and optimization process had 4 main steps. First, a fiber type was selected from the 3 we considered. Second, an initial value was chosen for the fiber volume fraction, the lamina thickness, the number of laminas, and the stacking sequence. Then, the loads were applied in the laminator software. If the failure criteria were not met, one of the variables was increased or changed to meet that criteria. If the criteria were met, one of the variables was decreased to lower cost, weight, or thickness. Then, step 3 with the loads in the laminator was repeated until optimal cost, weight, and thickness could be reached. At that point, the laminate details were recorded, and the process was repeated with a new fiber type. This flowchart lays out the testing and optimization process that I just described. Before research into the epoxy and the fiber types was completed, 12 stacking sequences were put through the laminator using some of the software's default composites. It gave a general idea of which stacking sequences were the best regardless of what the specific composite properties were. The 3 stacking sequences that performed the best overall were 0, -45, 90, plus 45 symmetric, 0, 90, plus minus 45 symmetric, and 0, plus minus 45, 90 symmetric. For our design composites, the 0, plus or minus 45, 90 symmetric composite was the best. With the T700S carbon fibers at 60% volume fraction and 8mm lamina thicknesses, the 0, 90, plus or minus 30 symmetric, 0, 90, plus or minus 45 symmetric, and 0, 90, plus or minus 60 symmetric stacking sequences were tested. The 0, 90, plus or minus 30 symmetric composite was the only layup that passed. This table shows the physical properties of 4 different types of composites that we looked at. For the first iteration, we used the T700S carbon fibers at 60% volume fraction. The 0, 90, plus or minus 30 symmetric composite proved to handle forces the best of all of them. The optimal thickness for each lamina was 7, 8, 7, and 7 millimeters symmetric. The upper 90-degree ply failed first, which caused the entire laminate to fail. Then the fiber volume fraction was increased to 80%. However, this made the 90-degree ply become even more unstable, so the 60% volume fraction composite was favored. Working with the result that the 60% volume fraction composite was the best, we moved forward to use the T1000G carbon fiber at 60% volume fraction. The 0, 90, plus and minus 30 symmetric composite once again was the most effective stacking sequence, and its optimal thickness for each lamina was 8, 6, 0.8, and 0.8 symmetric millimeters. The third and final iteration used pyrophil HR40 carbon fibers at 60% volume fraction. Once again, the 0, 90, plus and minus 30 symmetric composite was the most effective stacking sequence. The optimal thickness for each lamina in this composite was 8, 8, 3, and 3 millimeters symmetric. This table shows a summary of the 3 iterations using 60% fiber volume fractions for the 3 different carbon fiber types. It shows the most effective layup, the thicknesses, and most importantly, the weight and the cost per volume. While the T700S composite had the lowest cost per volume, the T1000G composite had the lowest cost per component and by far the lowest weight and thickness. So, our final design was a 60% volume fraction T1000G carbon fiber composite with that 105-205 epoxy. It was the lightest, cheapest, and thinnest option. The optimal layup was at 0, 90, and plus and minus 30 degrees symmetric. The optimal thickness was 8, 6, 0.8, and 0.8 millimeters symmetric. Due to the high modulus, the spar cap can be reduced to a very small thickness, which in turn made it the lightest and cheapest. The T700S and pyrophil HR40 based composites were significantly heavier, thicker, and pricier than the T1000G composite. Thank you for taking the time to learn about our design project. The next slide shows the breakdown of work between the group members. As shown here, we were able to successfully break up the work very evenly based on personal strengths and schedules.